3D models are defined by points in space called vertices, and to make them appear as real objects, we require the normals to the surface to calculate light reflection and shade the model. So how do we get the normals? Well, that's where the triangles come in. Let's focus on a single triangle, shall we? We represent the vertices by position vectors P1, P2, and P3. Let's also call the direction vector from P1 to P2 vector A. We calculate it by computing P2 minus P1. We do the same for P1 and P3 and we get vector B. To calculate the normal to the surface, vector N, we take the cross product of vectors A and B. But some of you might be wondering, why triangles? Why don't we just include an extra vertex point and use a quadrilateral as the fundamental shape for 3D models? Well, that's because all 4 points on the quadrilateral will not be coplanar, giving rise to an extra normal. However, in the case of a triangle, the 3 points are always coplanar. Also, any complex polygon could be divided into triangles. Hey, wake up. We still have a lot to show them, don't we? Let's start off a tangent here. Now that you know why we use triangles, it becomes easier to appreciate the efforts put by 3D software to abstract these low-level concepts into the cohesive tools that we use today. When designing game levels, one could decide to create all the 3D models in external software and then import them into the game engine for level design. However, this workflow is not always optimal due to the difficulty of implementing changes, creating and managing a large number of models, or implementing some game engine features. For this reason, a large number of game developers create software that run in the game engine's editor to assist with level design, 3D modeling, and several other complex development processes. We simply call this kind of software editor tools, and they speed up game development exponentially. Also, it's important to point out that for a 3D model, we call the collection of the vertices, edges, and triangles that define the model a mesh. Now let's consider a game designed with some expanse of land. Perhaps, due to the intended scale of the map, development would be much faster if we created a tool to generate mesh for the terrain. It is easy to generate random floating points in space for the vertices, perhaps by sampling some noise. But how do we generate the triangles for the mesh? How do we know which vertices make up a triangle? For all we know, if we pick the vertices for the triangle at random, we could end up with a mesh like this. Okay, this is a very terrible and unusable mesh. But let's say we're a bit smarter than this. Maybe we decide to look at just a portion of the vertices more closely. And we observe that the best vertices to form a triangle with are the ones closest to it. Perhaps we also devise a simple rule that edges must not intersect. Then we build the triangulation by adding the closest vertex point each time. So we end up with this mesh, but it just doesn't look right. We have some very long and slim triangles like this, or this one with even more acute angles. while some others are much wider. This is in contrast to many patterns we see in nature, which, while random, usually have much lower variance in size in a particular area. Maybe that's why this doesn't look right. Now let's look at the same vertices, but with a different triangulation. Wouldn't you agree that this looks a bit better? The triangles are more evenly sized and the mesh looks just a bit more natural. Also, if you had to perform a finite element analysis on the original mesh, which is a method for predicting how a structure would react to physical forces, it will give a less consistent result, as the whole process involves breaking a complex structure into much simpler elements and then computing the effects of the physical forces on each element. Of course, long or needle-like triangles like this would have more compression strength along the axis of its most acute angles, and less strength on the axis of the obtuse ones. This leads to the inconsistencies we see and less accurate results in general. Another issue with the original mesh is that of overshading. Okay, let's imagine that each box in this grid represents a pixel. In the rendering pipeline, pixels are not processed individually. They are usually processed in 2x2 blocks called pixel quads. This allows for things like derivative functions or computing map levels, and after execution, the extra pixels are discarded. This means that during the rasterization of a triangle, not only are the affected pixels processed, but the entire pixel quad. Now, long and thin triangles increase the percentage of pixels that are discarded, and this is called overshading, whereas a well-distributed triangle wastes less pixels, or in technical terms, we say it has a better quad utilization. And now you can appreciate the improved mesh for having a much smaller number of needle triangles. But what kind of triangulation do we have on the improved mesh? Well, the answer, as you must have guessed, is a Delaunay Triangulation, named after Boris Delaunay for his work on it in 1934. Let me explain. For every triangle, there exists a circle that touches all three corners of the triangle. We call this a circumscribing circle, or a circumcircle for short. Now, a Delaunay triangulation is a set of points with triangles such that none of the points lie within the circumcircle of any of the triangles. This means that if we were to shift this point to the left such that it entered the circumcircle of this other triangle, then the Delaunay condition becomes false and we no longer have a Delaunay triangulation. In the case of the original mesh, we can see that these vertices marked in red lie within the circumcircle of this triangle, and is so for many other triangles. However, in the improved mesh, no vertex point lies within the circumcircle of any triangle. So how do we perform this triangulation? Or how do we improve our original mesh? For the original triangulation, we can look through the edges of each triangle to check if the triangle, along with the neighbor, satisfy the Delaunay condition, that there is no vertex point within their circumcircles. If the condition is not satisfied, then we can flip the edge. The new triangles would satisfy the condition. However, flipping can also change the status of the other connecting triangles. So we do have to check those triangles too. And now we have our Delaunay Triangulation. Another popular algorithm is the Bowyer-Watson algorithm, as it performs the triangulation process without the complexities of flipping edges. To begin this algorithm, we first create a large triangle that fits all the vertices in consideration. We call this the super triangle, and we can get this by first finding the bounding box of the vertices in consideration. Then we can use this formula to get either the base or height of the triangle by varying the extra width x or the extra height y. Now that we have the super triangle, our next step is to loop through the vertices. And for each vertex point, we check if it lies within the circumcircle of the existing triangles. If it does, we delete that triangle. Then we create new triangles based on the edges of the deleted triangle and the vertex point. Good. Now we can go to the next vertex point and repeat the same. In cases like this, where the point lies within the circumcircles of neighboring triangles, we ignore the common edges when creating the new triangle. Perfect. We also observe this when checking through the next vertex point. And similarly, we ignore these two common edges and only use the edges on the perimeter to create new triangles with the vertex point. Now let's watch the remaining triangulation unfold. Finally, we delete every triangle that shares a corner with the super triangle. And we get this. Lastly, something to note. Throughout this video, I've only talked about Delaunay triangulation in 2 dimensions for simplicity's sake. However, the principle extends to 3 dimensions and even higher. The infinity is currently a one-man show, and it takes a lot of determination, creativity, and countless hours of effort to research and animate a video like this. So if you found the video interesting, or if you've learned something new, I'd be happy if you liked this video and subscribe to the channel. And I'll be eternally grateful if you subscribed to my Patreon to keep the channel running. Links in the description.